Okay, FIFAI 24 underscore 1, day 1. Okay. So this is the code you see here. So you just need to type it in here. You don't need to create an account. You don't need to sign up. So FIFAI 24 underscore 1. And then basically you will go to polls and you'll find the survey. The survey is on. So you should be able to complete it. Okay. So I'll give you a minute to do so. Perfect. Okay, cool. So if you guys have any questions regarding the RISE, our activities, if you have any suggestions, we would like to hear from you. So we'll collect some feedback at the end of the 3rd day on Sunday. And feel free to reach us also at rise.miccai@gmail.com. All right, so here I'm going to stop my screen sharing and share my Slido. All right. So the website is, you can type in slide.do or slido.com. And then the code is this one. So I hope everybody is able to join and complete this quickly. Okay, maybe 1 more minute or 2 more minutes. You guys need more time or all is good? Ayub, yeah? Okay, more time. Okay, we'll wait for a minute more and then we'll see the results of the survey. So just a reminder, if you are a lab lead, please edit your name and add lead at the start. So I can make you a co-host for the lab session that we have later. All right, so it means that you're presenting later. So I don't think you'll be presenting, Ayub. Okay, cool. So all right, so let's have a look at the results. Can I view results? All right, so we have a lot of people from Morocco. Oops, I was still interactive. UK, Uzbekistan, Tunisia, Spain, Nepal. That's very nice. Ethiopia, India, Chile. Very good diversity. Okay, nice. And then the time. Oh, different time zones. Oh, this is, I should have made it a word of cloud, but it's fine. Okay, so varying time zones. Your level at ML 3.5, okay, out of 5, that's very good. 85% no gradient descent. So I wanted to ask this question because the federated learning is based on that. So I'll share some resources with you guys if you don't know.
The first round.
Sorry, if you don't master gradient descent, you will not be able to I guess, grasp a lot of concepts that we will present during these 2 days. Okay, so federated learning, fairness, a lot of fairness in both federated learning. So, okay, so new computational methods, bias, experience bias, innovations, corporations, nice. Okay, cool. Great. So that was that. So that was a very just brief introduction about where you are, what you are doing, what you do. Okay, here. Oh, it's interesting. So 75% are students, 13% researchers, faculty, and others. Okay, sounds great. Welcome on board. Thanks, everybody. So I'll hand it over to back to Andrea to introduce the next session. Thank you.
Thank you.
Enjoy the summer school, guys. Thanks.
Thank you very much. And so now we will start with the first session. So it's Fair AI in medical imaging. And for that, it is my pleasure to present Dr. Andrew King. So Dr. King received a bachelor degree in computer science from Manchester University, followed by a master's with distinction in cognition, computing, and psychology from Warwick University, and has a PhD degree in computer science from Warwick University. Since 2006, he has worked in the School of Biomedical Engineering and Imaging Science at King's College London, focusing on machine learning and medical image analysis. So please welcome Dr. King.
Thank you very much. Can you see my slides okay?
Yes, we can.
Good. So thank you for the invitation and thank you for the introduction. It's a pleasure to be here today. I've always been a bit of a fan of RISE, so it's a particular pleasure to speak at this event. So this talk is going to focus on the topic of bias and fairness in AI, mostly focusing on medical imaging as an application. And I'm going to try and give an introduction to the basics of fairness in AI, what it means, why we should care about it, how we can identify it, and a bit about what we can do about it. So the idea is that this will give you enough knowledge to build on in the more interactive and practical parts of the sessions in the school. Now, this research field actually originated in computer vision and general machine learning. So I'm going to talk a bit about non-medical applications, but I'll then try to focus on applications in medicine and medical imaging in particular. So this is a brief overview of what I'd like to talk about today. So we'll start off by trying to set out the context in which Fair AI came into being and exists today. We'll then introduce some terminology that's important to understand when reading papers on fairness in AI. Then we'll discuss the potential role of Fair AI in a medical context. We'll have a brief tour of what I think are some of the key works on Fair AI in medicine. And then we're going to kind of revisit what we actually mean by Fair AI and try and sort of define it in a bit more detail, and a bit more precision. And finally, we'll close by providing a summary and some resources for future study. So before we start, I'd like to go over some learning objectives. So at the end of this session, you should be able to explain the meaning of fairness and bias in AI and describe why it's become an important issue recently. Explain some fairness definitions using common terminology for talking about bias in AI. Explain some approaches for addressing or mitigating bias in AI. To discuss some papers on fairness in AI in medicine and beyond. And to describe the differences between Fair AI in medicine and other applications. So let's kick off then. So before I talk about bias and fairness, I'd actually like to take a bit of a sidestep and talk more in general about what AI models actually are. And hopefully this will help us to understand a bit better why the field of Fair AI exists at all, and also why it's actually not existed for very long. So I'm sure we've all heard the term black box when it comes to AI and deep learning in particular. But what do we mean by this? And is it something we should be concerned about? So thinking about what AI models do, all models can be viewed as taking some data as input, as you can see on the left here, and producing something as output on the right. The details of the input and the output will depend upon the model and what problem we're trying to solve. The details of how the input is mapped to the output will depend upon the type of model we're using. So it could be something simple like a linear regression or a decision tree, or it could be something more complex like a deep learning model. Now, these are obviously different types of model, but they're different not just in terms of how they work, but in how much we as developers and users of AI can understand what they're doing. So when we talk about a black box model, we mean one which cannot be easily understood or inspected by a human. So basically, we can see that an input is mapped to an output, but the process through which this happens is quite opaque or quite difficult for us to understand. So let's think a bit more about what we mean by this. Now, in fact, it's actually quite unusual for AI models to be completely opaque. So usually we can inspect the details or the parameters of the model. So they're generally not completely hidden from us. For example, we can usually look at the weights of a neural network, but what will we learn from doing so? In this case, hopefully you'll agree, not very much, it's just a bunch of numbers. So this brings us back to our definition of a black box model. It's a model that cannot be easily understood or inspected by a human. In this case, we can inspect it, but we can't really understand what it's doing. In other words, it's the complexity of these modern AI models that makes them black box. So then we can ask ourselves, is this the case for all AI models? Are all AI models black boxes? And this introduces the concept of what's known as a white box AI. So as an example of a white box model, we can see here a simple decision tree. And the task of this decision tree is to prioritize bed allocation for hospital patients and urgent care patients. And this is a completely made up example, by the way. But the point is that we can see how this model works by starting at the top of the tree, working our way down and answering questions using the input data to the model as we go. And incidentally, if you're wondering, injury severity score is a number that's assigned to an injured patient based upon how bad their injuries are. The important point to note here is that it's quite easy for us to understand how this model works. So we can say that it's white box or sometimes interpretable or explainable. And I think we can agree that this type of visualization of the AI model, the decision tree, is much more understandable by humans compared to the weights of a neural network that we can see here. And it might be that these weights do exactly the same thing as the decision tree. So just to recap, we refer to models that can be more easily understood by humans as white box models, and white box models can be beneficial in terms of promoting trust amongst end users. People are much more likely to trust something if they can see how it works. In other words, they can see how the inputs are mapped to the outputs. We can also, as I said, we can call these models interpretable or sometimes explainable. There's not really universally agreed definitions of these terms, but in general, they mean just more understandable to us. So an important question to ask is, why are these types of model generally seen to be a good thing? Okay, so let's revisit this application of prioritizing bed application. And we can see here two different models are doing the same thing. A decision tree on the left, which as we just discussed is a white box model, and then a complex neural network on the right, which is a black box model. And let's say that these two models do exactly the same thing. So they will make exactly the same decision for every patient as to bed allocation priority. So let's ask ourselves which one is preferable. So if you just take a few moments to look at the one on the left and at the one on the right, if you want to as well, and just think about if you have any concerns about either of these models. So hopefully what we can all easily see is that the white box model is completely racist. If we look at the top node in the tree, it clearly prioritizes white patients over other races, which I hope we all agree is not a good thing. But the important point is that we can easily see this. And we can't see this in the black box model on the right, which is also racist because it has exactly the same behavior as the white box model. So one benefit of white box AI is uncovering the potential for bias in AI models. Another point is that it's also quite easy to fix the bias in the white box model. We just remove that racist top node in the tree. But how would we do that for the black box model? How would we go about modifying those weights to make it less biased? So white box models enable us to more easily uncover this bias or toxic behavior, and also to address and remove it. So now we've got a bit of a problem. We'd like to use the best performing models, especially for complex problems, but these best performing models are often black box models, like deep learning models. And we know now that black box models may suffer from bias without us realizing it. So what can we do? Well, this is where fair AI comes in. So one way of describing fair AI is as a set of techniques that allow us to assess and potentially address bias or toxic behavior in black box AI models. Now, fair AI is a fairly young field, and now hopefully we understand why. Until relatively recently, it was much more common to use simpler and more interpretable models. Since the advent of complex black box models like deep learning, we've seen two main changes. First, there's been a significant improvement in performance, and second, there's been a significant reduction in interpretability or explainability. Now, fair AI is in large part a response to the second point. It's trying to help us know if a black box model is biased. But it's also partly a response to the first point. Deep learning models perform very well, but they're also very good at finding shortcuts to maximize their performance. And shortcut learning can arguably make deep learning models more susceptible to bias than simpler white box models. For example, when diagnosing a disease, it could use features related to different groups of patients based upon their sex or their race instead of the actual disease phenotypes, and that would be bias. So let's talk now a bit about the history of fair AI. So there was a landmark paper called Gender Shades in 2018 that was instrumental in raising awareness and interest. It's now been cited more than 6,000 times in the last 6 years since it was published. Now, I'm not saying this was the first ever paper on fairness in AI, but it was very high profile and it generated a lot of interest in public and researchers alike. The paper investigated race bias in commercial gender classification models. So models that would tell a subject's sex from a video picture of them. And they found that performance of these models was significantly worse for non-white subjects. And the authors argued that the reason for this was that the imbalance in the training data used to train the models. They were trained on mostly data from white subjects. Now, as we just said, AI is quite good at using any trick it can find to maximize performance. So if we specify via the loss function that we just want to maximize overall performance, regardless of, for example, race, and one race has many more subjects in the training set than the others, then the models may learn features that are specific to that majority race and ignore the minority races. And that might well improve performance on the majority race, but will also have a detrimental impact on the minority race. But in terms of overall statistics, overall performance, it will be doing well. So this seemed to be what was happening in these commercial AI models. And as an aside, both authors of these papers have gone on to become quite well known in the field. So Joy Buolamwini has had a Netflix documentary made about her work on algorithmic bias, and she now runs the Algorithmic Justice League. And Timnit Gebru was in the news after being sacked by Google a few years ago for apparently highlighting the lack of fairness in some of their AI systems. And she now runs DARE, the Distributed AI Research Institute. Andrea, you've got your hand up?
No, sorry, it was a mistake. Sorry.
Okay, sorry. So she now runs DARE, the Distributed AI Research Institute, which is an organization aiming to promote the responsible use of AI. So both are still strongly involved in campaigning for the fair and responsible use of AI. So a more recent example of bias in AI comes from OpenAI's DALL-E 2 text-to-image generation software. So this is an AI model that takes free text as input and uses a generative model to produce images that are representative of the text. And the pictures here show images produced when asked to show what lawyers and flight attendants look like. And we can see that the model is biased because it thinks that all lawyers are old white men and all flight attendants are young women. So the reason for the bias here is likely the same as in the Gender Shades paper. Data in the real world are biased. So using these data to train AI can lead to biased models. So now we know a bit more about what fair AI is and why it exists. So before we proceed further and talk about its role in medicine, I'd just like to introduce some definitions and terminology of fair AI that would be useful in understanding the rest of the material. First, we can make an intuitive definition of fairness that I think we can all understand and relate to. We can say that in the context of decision-making, fairness refers to the absence of any prejudice or favoritism towards an individual or a group based upon their inherent or acquired characteristics. So when we talk about bias in AI models, we're typically referring to this favoritism. which means different levels of performance for different individuals or groups. Now, what we mean by performance can vary, but typically it means, for example, the accuracy of a classifier or a regression model. So we're talking about, an example could be a classifier having higher accuracy for men than for women or vice versa. Note also that I'm talking here about techniques for addressing bias. In computer vision, people often talk about mitigating bias, implying that it's something that we can and should make disappear completely. I think in medicine, as I'll discuss later, things can be a little bit more complex than that. So let's introduce some terminology. By a protected attribute, we mean the characteristics for which we want to ensure fairness, for example, race or sex. And this is also sometimes called the sensitive attribute. And a protected group is a group of subjects who share the same protected attribute value. So, for example, women could be a protected group or men could be a protected group. And finally, note also that I think the term fairness is actually slightly tricky to define, but in general, we're talking about addressing any bias that's been found. So a fair model is one that has less bias. I'll be a bit more specific about this in a couple of slides' time. So in the last slide, we saw that bias refers to different levels of performance between protected groups. But what do we mean by these differences, and what do we mean by performance? So in other words, what does it mean to ensure fairness in an AI model? So at first it might seem obvious, but actually there are multiple ways of defining fairness more formally. So to illustrate, I'd like to give some examples to show the types of things that need to be considered. And let's consider this in the context of a classification problem. For example, AI-based diagnosis of breast cancer from some patient imaging data. Our protected groups are going to be white subjects and black subjects. And in the following slides, I'll introduce some definitions of fairness. And in doing so, I'll refer to the numbers of true positives, true negatives, false positives, and false negatives of our classifier. So these can be computed, as shown on the right here, using knowledge of the AI predictions, which is the horizontal axis, if you like. Sorry, the vertical axis. And the ground truth diagnoses, which is the horizontal axis, as we can see in the table there. So true positives are obviously when the ground truth is true and the prediction is true, and so on. So the first definition I'd like to introduce is called equalized odds. In plain English, we have equalized odds when the probability of a person in the positive class being correctly assigned a positive outcome and the probability of a person in the negative class being incorrectly assigned a positive outcome should both be the same for the protected groups. So in other words, whether you're correctly diagnosed or not does not depend on your protected group. So black and white subjects with and without breast cancer will have the same chance of being diagnosed correctly by our AI system. More formally, we can say that the AI classifier should have equal true positive rates and false positive rates for white and black subjects. So again, referring to the table on the right, the true positive rate is equal to the number of true positives divided by the total number of positives or patients with breast cancer. And another term for this is sensitivity. And the false positive rate is the false positive divided by the total number of negatives or patients without breast cancer. And this is equal to 1 minus the specificity. So to test the fairness of our AI classifier, according to equalized odds, we would calculate the true positive rate and the false positive rates separately for each of the white and black subjects and simply compare them. And if they were different, then that would be a violation of equalized odds. Another definition of fairness is known as demographic parity. This means that the likelihood of a positive outcome should be the same regardless of the protected group. In other words, both white and black subjects should have an equal chance of being diagnosed positive for breast cancer. More formally, we can define the number of the predicted positive rate as simply the number of positive predictions by the classifier divided by the total number of subjects. And note that this is based purely on the classifier outputs, not anything to do with ground truth values. So to test for fairness according to demographic parity, we will calculate the predicted positive rate for white and black subjects and compare them. So this is a nice illustration because in this case, in the case of breast cancer, this assumes that white and black subjects have equal prevalences of the disease. If this is not the case, when trying to ensure demographic parity, might actually end up having a detrimental effect on model performance. So, for example, if white women had a lower prevalence of breast cancer, trying to ensure demographic parity would actually increase the number of positive diagnoses for white women, which means adding more false positives. Alternatively, you could decrease the number of positive diagnoses for Black women, but that would mean adding more false negatives and misdiagnoses. So you have to think carefully about what type of fairness is appropriate in a given situation. And finally, we'll look at equal opportunity. So equal opportunity states that the probability of a person in a positive class being assigned to a positive outcome should be equal for both protected groups members. Now, the chance of a person in the positive class being correctly diagnosed positive is also known as the true positive rate or the sensitivity, and we saw this already in the definition for equalized odds. So equal opportunity is really just a slightly less strict version of equalized odds, and it just looks at the sensitivity instead of sensitivity and 1 minus specificity, as we saw before. More formally, we can compute the sensitivity using the formula shown here, which is the same as on the earlier slide. So these are 3 commonly used definitions of fairness, and we've seen that they all try to ensure fairness in slightly different ways. There are actually other definitions, but I'm not going to go into detail here. I just want to get over the idea that there are different definitions for fairness, and that each might have a role to play in different scenarios, but you should think carefully about what role is appropriate for your scenario. There's a reference here that would have more details of the different types of fairness. So now we know about different ways in which fairness can be measured. And in a minute, we'll talk about things that we can do to improve fairness. But let's think first about why AI models can become biased in the first place. So as I mentioned a few slides ago when I spoke about the Gender Shades project, often but not always, bias results from underrepresentation of certain groups in the training data of the AI model. For example, we can see here the race breakdown of the well-known UK Biobank dataset. And as you can see, it's mostly white, like the UK population was at the time that it was started. Now, if there's some kind of difference between the data acquired from different races, this underrepresentation of non-white races can cause models to perform better on the overrepresented groups and worse on the underrepresented groups. For example, the differences could be related to anatomy or relative incidence of pathology or other factors. But just to re-emphasize, this is what we mean by bias, a model performing better for some groups than others. And if these differences are significant, and these AI models are used in clinical care, this can be viewed as a form of discrimination because some groups will receive worse care than others. So what can we do about bias? This slide shows 3 categories of approach for addressing bias and hopefully ensuring the fairness of AI models. And the 3 categories are based upon intervening in the 3 different phases of AI model development and deployment. First of all, preparing the data. Secondly, training the model. And finally, using the model on test data, which we can call model deployment. So first, the first column, pre-processing techniques, focus on preparing or curating the data used to train the model. Second, in the middle column, in-processing techniques focus on the way in which the model parameters are learnt using the training data. And finally, post-processing techniques focus on modifying the outputs of a model which might be biased after it's been applied to the test set. So in the following slides, I'm going to discuss a few different sample approaches from each category. So first, pre-processing techniques. So we said a couple of slides ago that often, but not always, bias in AI models results from an imbalance in the training data used to form the model. So the most obvious thing to do is just to add more data for groups that are underperforming and then retrain the model. So the figure shown here illustrates the effect on AI-based cardiac MR segmentation performance of increasing the number of Black subjects in the training set. So the green box plots are the performance of the model on white subjects, and the orange ones are performance on Black subjects. And as we go from left to right, we add more Black subjects to the training set. And as we can see, performance for Black subjects increases. So somewhere between the 2 extremes, so the left extreme is entirely white subjects and the right extreme is entirely Black subjects. Somewhere in between those 2 extremes, there's likely to be a kind of a sweet spot where the model will be fair according to some definition of fairness. So this type of effect has been illustrated in a number of applications now, but it's not always possible to add more data. Often we're working with pre-existing databases which are heavily imbalanced, and we just need to work with the data we have. So in such cases, we can add more data using other techniques, such as data augmentation. You can apply more augmentations to the underrepresented groups. An alternative approach is to use something called reweighing. So in reweighing, we address imbalance in the training set by applying a relative weighting to training samples based upon their group. So we effectively weight more highly samples from underrepresented groups. And this has the effect of increasing their importance in the training process, which can counteract the effect of their underrepresentation in the training data. So to go back to the UK Biobank data set from a couple of slides ago, we could apply a higher weighting in the training process to the non-white races, which would lead to their data having a larger effect on the learning process of the model. Alternatively, we could oversample from the underrepresented groups. So when we sample from the training data to form a mini batch during training, we make it more likely that samples from the underrepresented group will be chosen. So effectively, even though the training data as a whole are imbalanced, what the model sees of the training data is more balanced. So we can see some results of applying this technique here highlighted in green, again for cardiac MR segmentation. So the top row of numbers is the baseline. So the baseline is the normally trained model, and the second row is the oversampling approach. We can also call this, in that work, it was called stratified batch sampling. And as we can see, it increases the performance of the non-white races, and the model overall is more fair. Another example of a pre-processing approach to fairness is the SMOTE algorithm, synthetic minority oversampling technique. Now, SMOTE is actually a technique used to address class imbalance. So, for example, if you train a dog and cat classifier with many more dogs than cats, the model will focus its efforts on predicting dogs correctly, and it may not do as well on cats. Now, SMOTE works by creating synthetic samples of the minority class by interpolating between existing samples. So the figure here shows the steps involved. So first, in the first step, you select a random sample from the minority class, which are the green points in the image. Then you choose one of its neighbors and create a new synthetic sample by combining the two in some way. These are the red points in the second image. And finally, you repeat until you have enough samples for the minority class, as you can see on the right there. Now, this idea can be applied to fairness by applying it to boost the representation of minority protected attributes instead of, or as well as, minority classes. And there's a reference there that describes how to do that. So now on to in-processing algorithms. So with in-processing algorithms, they generally work by modifying the loss function of the model to try to ensure or encourage some aspect of fairness. An example of this type of approach is something called the meta-fair classifier. So here we co-train a model for the intended task and also a classifier to predict which protected group the subject came from, for example, sex or race. So the intention here is to make the main task model more aware of differences between groups and optimize its performance accordingly. So we can see some results for this method on the same cardiac MR segmentation task we discussed on the previous slide. Again, we can see that the meta-fair classifier highlighted in green improves performance for the underperforming groups and makes the model more fair. These are dice coefficients, by the way, of the segmentation model. Another example is a class of approaches which we can refer to as representation neutralization. Now, as the name suggests, these try to encourage the internal representation of the model, such as the latent space of a deep learning model, to contain no information about protected attributes. Now, this can be done in a number of ways, but one way is to use an adversarial training and have an adversarial classifier that tries to predict the protected attribute from the internal representation. So the idea of this is that if the model knows nothing about the protected attribute, it won't be able to discriminate. And finally, there are a number of works that have explicitly included a measurement of fairness into the loss. So a widely used example of this type of approach is called group DRO, which stands for Group Distributionally Robust Optimization. And this aims to minimize performance differences between protected groups. And as I say, it explicitly encodes that into the loss function of the model. And finally, let's see an example of a post-processing algorithm. So this works for classification models. So for classification models, the final decision is always based upon a thresholding of a probability. For a binary problem, this will be the probability of being in the positive class. And this probability can be chosen by looking at an ROC curve, like the one you can see on the left here. Each point on an ROC curve represents a different threshold, and a good classifier will be close to the top left of the plot. So it would have a high true positive rate and a low false positive rate. Now, in reality, an unfair classifier would have different looking curves, different looking ROC curves for each protected group. That means that's where the bias comes from. And that's shown here as the blue and the green curves. This means that their optimal thresholds will be different. And if you choose an optimal threshold, a single optimal threshold, it will introduce bias. So post-processing techniques can work by finding a threshold that aims to maximize fairness according to some definition, such as equalized odds or equal opportunity. So you can see that a lot of work has gone into addressing the biases that have been found in a range of applications in quite a short amount of time. The gender shades paper was only published in 2018, so it's only 6 years ago. So fair AI has become a very active research field in computer vision and general machine learning. But to be honest, until recently, it was much less so in medicine. And that's what I want to move on to next. So now, hopefully, we kind of know what fair AI is, although I'm going to return later on to exactly what fair AI is and isn't later on. Hopefully, we can also see why we need fair AI now, and in particular, why it's become more popular recently. So let's talk a bit about how it can be useful in a medical context. So before we discuss whether AI in medicine is fair, I'd like to review how modern medicine works in general, without thinking specifically about AI. So before AI came along, treatment and diagnostic guidelines have been typically established through research studies and larger scale clinical trials. The aim is to develop treatments that are effective for the population as a whole. But in general, these studies don't work with the whole population because it's just not feasible. Instead, we take a sample of the population under study, and that results in a health data set. And it's based upon that health data set that the findings will be based. In a research study, some characteristics of the subjects in the data set, for example, different types of treatment, are assessed and linked with outcomes or responses to treatment. And if successful, this proceeds to a larger scale clinical trial. And if this is successful, we have a new treatment or set of clinical guidelines, which can then be applied to the population as a whole. And in general, this scientific approach has worked well for the past 100 years or more. And this is why we have the advances in modern medicine that we have today. But now let's take another look at this process. But this time, let's say that our health data set is unbalanced. For example, mostly men with few women. So we go around the same process as before, but this time the results are based upon data from a non-representative sample of the population. So you can see in the health data set box there, it's mostly men and a single woman in that case. So we could end up with a treatment or a diagnostic tool that's effective for men, but could be less effective for women. And the same goes for other subgroups, such as races or age groups. And this would obviously be a cause for concern because it just wouldn't be fair on the underrepresented groups. So now the bad news. Actually, that hypothetical situation of sex and race imbalance that we just described is to a significant extent the current reality of modern medicine. Modern medicine is already unfair. There are many diagnostic treatment guidelines which were based on studies performed largely on white people from developed countries and often predominantly on men. For example, there's a few quotes on this slide from recent studies into healthcare disparities. The first one is from the Institute of Medicine in the United States. They say that race and ethnicity remain significant predictors of the quality of healthcare received. Second one also from the Institute of Medicine, this time regarding sex. They say that medical research historically has neglected the health needs of women. And finally, from Circulation, which is a well-respected cardiology journal, they say that steady improvements have been made in the management of cardiovascular disease over the last decade, yet certain racial and ethnic minority groups have not experienced equivalent improvements in outcomes. Now, there are many reasons for these inequalities, and it's certainly not as simple as just saying that all of them are due to imbalanced data sets, but it is recognized that this is one of the main contributors to the current situation. So these imbalances, combined with known physiological differences between sexes and races, mean that the diagnostic and treatment tools are targeted to work well on a subset of the population, but they may not be so effective for other less represented groups. And this is partly what leads to health inequalities. So this is a talk about AI. Why am I talking about modern medicine without AI? Why am I saying all this? Well, I want to make this point because I think to understand the role of AI in healthcare, we need to first understand that modern medicine is already unfair. So we're not dealing with a situation where AI needs to come in and maintain a fair situation, but rather we can see it as an opportunity for AI to come in and make modern medicine more fair and to address some of these inequalities. And again, this is where fair AI can have a role to play. So this is now just a reimagining of the pipeline we saw before, this time focusing on race imbalance. Now we can see that we again start off with a health data set, which may still be imbalanced, but this time we also store information about the races of the subjects, or demographic information more generally. Then we go around the pipeline as before, but when deploying the new technique, we can use a fair AI approach that can model the differences in race and perform analysis to ensure good performance for all subgroups. This could be one of the methods for addressing bias that we saw a few slides ago. Then again, we move on to a clinical trial, a new treatment or diagnosis, and finally a fair technique that will benefit all patients equally. So this is the dream, and what I'd like to do for the rest of this talk is to try and review in a bit more depth some of the important research that's been done to try and make this dream a reality. Right, so now we've covered all the basics, so we'd like to give a brief tour of what I think are some of the more important papers on fairness in medicine and medical imaging in particular. So first, let's review the scale of the literature in this field that we're dealing with. So this is quite an unscientific summary based on my own limited knowledge and experience. So I've split it into papers on bias assessment and papers on addressing bias. So fair AI is a young but quite big area in computer vision and general machine learning. There's been lots of work on developing novel mitigation strategies, much of it for non-imaging data, but also for imaging data. In medical imaging, there's been much less, in particular when it comes to addressing the bias. And perhaps the reason for this is that it's not quite so clear what we mean by fairness in a medical context, and I'm going to come back to this later. But it is clear that fairness in medical imaging is quite an underexplored area so far, which is, to my mind, surprising, considering the high impact that unfair models could have, AI models could have in medicine. So, for example, it could be missed or late diagnoses, inappropriate treatment, and so on. It's obviously important to have fair models in computer vision, but it's not usually a matter of life and death. And in medicine, it literally can be a matter of life and death. So let's go over some of the key papers. So this is just a very personal reflection on what I think are some of the important ones. So I think the starting point for any attempt to ensure fairness is to measure the performance of existing models for different protected groups. And this is actually not as common as you might think. I would say it's still the case that the majority of papers on AI for medical imaging do not report results broken down by protected groups. But here's one early example of a paper that did do this. They assessed an AI model for detecting heart problems from ECG traces. And I think this kind of reporting should act as a model for other papers going forward. Even if they're not papers specifically about fairness, I still think it's important to report data for different protected groups. I especially like the closing message of this paper. They said, we recommend reporting of performance amongst diverse ethnic, racial, age, and gender groups for all new AI tools to ensure responsible use of AI in medicine. I think hopefully we all agree with that. The next paper is not really about bias as such, but it's still highly relevant to the problem. So Judy Gichoya and colleagues found that AI models can be trained to predict subject race from a range of medical imaging modalities, including chest X-ray, CT, and breast mammograms. And the reason for this seems to be down to some kind of distributional shift in the imaging data between races. There's something about the image characteristics that's different between races. For example, it could be anatomical differences. If that distributional shift exists, then it can potentially lead to bias in classifiers trained for other tasks. And that's why this paper, I think, is important. Note also that being able to detect race from images, it just means there's a distributional shift there. It doesn't necessarily mean there will be bias in the AI models, but it means there's at least the potential. And if the nature of the features in the images is different between races, then a classifier trained on racially imbalanced data might learn to make more use of features from a majority protected group than from a minority one, and that would lead to different levels of performance or bias. This next paper was from MICCAI a few years ago. I think this was one of the earliest papers to highlight the potential for bias in AI models for medical imaging. That's why I chose this one. So the contribution of this paper was partly to highlight the lack of reporting on bias, again, just like the one a couple of slides ago, but particularly in medical imaging here. And partly also to highlight bias in a specific AI classifier for video images of skin lesions. They also demonstrated a simple bias mitigation scheme by multitask training. So the main diagnostic task and the protected attribute classifier, similar to the metaphor classifier idea I mentioned earlier. Now, a couple of papers that I'd like to discuss together. These are about bias assessment in chest X-ray classification. Chest X-rays were one of the earliest examples found of AI bias in medical imaging, and still probably the most active research application. In both of these papers, they trained AI models for diagnostic classification tasks using imbalanced data sets. And then they assessed performance by protected group. And they found bias by sex, age, and race groups. And the Lara paper on the left did a nice systematic study where they varied the level of imbalance and observed the change in performance, a bit like the AI cardiac segmentation plot that I showed you earlier. So in this figure, the horizontal axis is the percentage of females in the training set, and the vertical axis is classification performance for male subjects. So we can see that as the proportion of males decreases, as we go to the right, their classification accuracy also decreases. And a similar story was found for females. Next, I'd like to mention a few papers on bias in brain imaging. So this is an emerging area with just a few papers so far. And the story is a bit inconclusive so far. The first paper, top left by Stanley et al., shows different performance in sex classification by race from brain images. The second paper by the same authors tried to debias these classifiers. The third paper, top right by Peterson et al., found little to no bias in a model for Alzheimer's disease detection. And the fourth model by Wang et al. Found bias in brain imaging classifiers, but they also highlighted that choices of pre-processing and model training can significantly mitigate the observed bias. So I think this is a changing landscape and more work is needed in this area, but it seems as if the presence of bias might be task dependent, as the tasks addressed in these papers were not always the same. Bias in AI-based segmentation is a new area that's just opened up relatively recently. And this is, I think, a rare example of medical image analysis getting there before computer vision. So really, there had been no work on bias in segmentation in general machine learning or computer vision. And perhaps that was because segmentation is a much more relevant problem for us in medical imaging than it is in computer vision. Oops, sorry. Bias in segmentation manifests as different levels of performance for AI segmentation models for different groups of patients. And so far, this bias has been found due to race and sex in cardiac MR and brain MR segmentation, as well as by race in skin lesion segmentation. That's what these papers are about. Okay, so I started off this section with a summary of how many fair AI papers there were in computer vision and medicine, but how is this changing? So I did a slightly more scientific survey, this time using PubMed. So these are medicine-related papers only. And the search criteria were either fairness or bias, and either AI, deep learning, or machine learning in the title of the paper. And I found 239 hits in total. And there are probably a few false positives in that total, but it's really noticeable that there's been a very significant upsurge in the last few years. When I did the same search about a year ago, it was 122 hits. So it's roughly doubled in the last year. So I would say if you're thinking of getting involved in fair AI, now is certainly a good time. Okay, so we've talked quite a bit now about fair AI, and we've tried to define it in simple terms. But now I'd like to revisit this and talk a bit more about exactly what it is and also what it isn't. And the first thing I'd like to discuss is the relationship between fair AI and domain shift. So I've mentioned a few times already the idea that bias can be caused by demographic domain shift or distributional shift between protected groups. So first, let's review what we mean by domain shift in general. Because domain shift is a known problem in many medical imaging applications. It's not just in fairness that people talk about domain shift. It can cause a drop in performance at test time if the test data or the target data have a domain shift from the training data or the source data. For example, there are several public data sets in computer vision to allow researchers to assess and mitigate the effects of domain shift. There's one here, the Office Home data set contains images of everyday items in 4 styles: real world, product, clip art, and art. Shown here is just 4 images of a mug. The PAX data set stands for picture, art, cartoon, sketch, and shown here is 4 pictures of a dog. And in both of these data sets, clearly the semantic meaning of the picture is the same. It's either a mug or a dog. But the style is different. So there's a domain shift between the different types of images. And if we trained an AI model on photos of dogs, it wouldn't work as well on cartoons of dogs. So state-of-the-art AI is known to be quite brittle in this regard. In other words, it doesn't generalize well across domains. So these were from computer vision, but the same is known to be true in medical imaging. Here we can see differences in intensity profiles between MRI sequences and scanners. They're all pictures of brains from MRI, but you can see their characteristics are quite different. And techniques for so-called domain adaptation or even domain generalization have been proposed. So this is it's a well-studied area, domain shift and domain generalization. So coming back to fairness, we've already seen that similar domain shifts exist due to demographic protected attributes. For example, the Gichoya paper showed that AI can detect race from medical images, so there must be some kind of domain shift there. So now the question I'd like to ask is this what we mean when we talk about fair AI? Is it just another form of domain shift? So I would say to a certain extent, yes, it is about demographic domain shift, but I also think it's much more than that. So this slide shows a typical pipeline of AI in healthcare. Now, maybe most work on fair AI focuses on that middle box there in green, on the model training. And here what we're talking about is mostly a problem of demographic domain shift and how we can deal with that. But bias can be injected into the healthcare AI pipeline at many other points. And fair AI is about addressing all of these, I think. For example, we need to think carefully about how we define the problem we're trying to solve, how we collect the data, and what data we collect, how we pre-process the data, and how AI is used in downstream clinical workflows. Bias can exist in all of these places. AI does not exist in isolation. It's embedded in a healthcare system, and this system has its own biases, as we saw earlier. Modern medicine is already unfair. So if we ignore this, we will never solve the problem of fairness. So I would argue that whilst demographic domain shift is a large part of fair AI, it's not all it is. It's much broader than that. I would also argue that a lot of work has gone into addressing other forms of domain shift, such as MRI scanner differences, but demographic domain shift has been much less investigated. So it is still worth investigating that center box. But I would say don't just investigate the center box. So I think we're getting closer to knowing what fair AI is now and its scope, but we've talked mostly so far about uncovering bias and not so much about what we should do about it. And I think this is actually a harder question than you might think. So to illustrate this, I'd like you to consider 2 case studies of different scenarios in terms of fairness. First, in computer vision. It's common that we know nothing about the subject before model inference in computer vision. For example, in facial recognition models, by definition, we don't know who they are before they're recognized. So in this scenario, we want to make performance as equal as possible between protected groups. This seems fairly uncontroversial to me. And much work in computer vision has aimed to remove any trace of the protected group from the internal representation of the model with the aim of mitigating these biases. And that's, as I said earlier, that's an approach known as representation neutralization. This technique came from computer vision, where it is appropriate. In medicine, I think it's quite different. So, for example, doctors routinely make use of protected group status, such as sex and race, when making diagnoses. And they would consider it foolish to ignore that information. So why should we try and get AI to ignore it? Also, it's possible that bias mitigation schemes might harm some protected groups and harm them knowingly, since we may well be aware of protected group status at inference time. And this brings us to the ethical principle of do no harm. So in medicine, the term non-maleficence refers to this principle of first do no harm, which is the foundation of modern medicine. No doctor would give a treatment to a patient if they knew it would worsen their condition. For example, look at these results from some work that analyze different levels of performance for different races in AI-based cardiac segmentation. So this is the example that we saw earlier on when I was showing the bias mitigation techniques. This table shows the DICE scores for the predicted segmentation. So a high value is good, and a value of 1 is a perfect segmentation. So first, the top row shows the results for the naively trained model using standard learning approaches, and we can see that there are differences in performance between the different races. This model was trained using mostly white subjects from the UK Biobank, and the performance is best for white subjects, as you can see. The next 3 rows are for different ways of trying to reduce this bias and equalize performance between races. And it does that quite successfully. In terms of fairness, it improves fairness. But look what happens with white subjects. Their performance gets worse when we mitigate for bias for all 3 techniques. So if you think about it, we could be knowingly harming them by addressing this demographic domain shift. And that could violate the principle of non-maleficence. We're doing harm to the majority group. And this is not something that comes up in most other forms of domain shift, and certainly not in computer vision. So there are important ethical considerations when dealing with demographic domain shift. They're quite unique in medicine, I think. Now, I'm not going to try and answer what we should do in such cases here, but I just want to highlight that the problem of bias mitigation in medicine is not quite as straightforward as it often is in computer vision. And I really believe we should be having a wider conversation about these ethical issues regarding fair AI in medicine. And there's actually not been that much focus on these issues so far, but I'd just like to highlight a few exceptions in a bit of a literature review here. So first, there's a couple of papers which have discussed potential ethical issues associated with fairness in a medical context. So I'd recommend these 2 papers by Melanie Gantz and Enzo Ferrante's groups. And a couple of things I've been involved with myself. There's a blog, well, couple of blog posts on the top there, and a podcast that I was involved with where we discuss these things. So you can check those out if you like. Okay, so that brings us almost to the end. So I'd just like to summarize and review some useful resources on bias and fairness now. So to summarize, we've seen that fair AI is basically looking for ways to assess and address bias or toxic behavior. And by this, I mean discriminating against certain protected groups. Note the word address and not mitigate. One of the major challenges in fair AI for medicine is that it's not always clear what, if anything, we should do about the bias. This makes it quite different to fair AI in computer vision, where I think it usually is clear that we just want to eliminate or mitigate the bias. And when we try to address bias, we need to remember that this is not just a question of addressing demographic domain shift. We need to look at all parts of the healthcare AI pipeline. We need to start right from the beginning, where we define the problem we're trying to solve and determine what data will be collected and how. There's the potential for bias everywhere. And there's still a lot more to do. Investigating new applications for bias, assessing and understanding if and why some models are more susceptible to bias than others, looking further at the interplay between different types of domain shift, looking into ways to address bias without knowledge of protected group status, and there's many other areas as well. There's no shortage of problems to look at. There's just a shortage of researchers to look into them, in my opinion. So I just also like to give a couple of closing messages here. First, I think it's really important that as AI developers, we should consider how AI should be implemented in medical imaging, or even if we should. We shouldn't just do it because we can. We should aim to implement AI where it's clear that there will be patient benefit, but we should also think carefully about what its role will be in the clinical workflow and what characteristics we want it to have. If we do think there will be benefit, we should consider who will benefit, and more importantly, who will not or will benefit less. So the techniques need to be fair. And most importantly, I think let's be open about all of these things. People will not trust AI or AI developers if they get the impression that we're not being open and transparent about the limits of performance of our models. And I'm talking here not just normal performance metrics like overall accuracy, but also fairness metrics. Reporting of demographic bias in particular needs to become the norm rather than the exception. So if this talk has made you interested in fair AI, then there's a number of free resources for you to make use of if you want to start looking into this kind of research. So you don't have to start from scratch. AI Fairness 360, Fair Learn, and Equitas and Medfair are all toolkits that might be useful to you in your research, and they're all free as far as I know. And there are many unexplored areas in fair AI for medical imaging. So now, as I said, is a very good time to get involved. Likewise, there are several initiatives aimed at addressing issues related to AI bias. So there's the Future AI project, which is an EU-funded project to establish a set of guiding principles for future AI development in healthcare, including fairness as one of its 6 key principles. Standing Together aims to promote diverse data sets and to reduce bias in modern medicine, including AI-based techniques. And then FAMI, which is a group of academics who are interested in fair AI for medical imaging. They run workshops and free online events, including this one. So I'm involved in this. Esther and Tiarna, the other organizers of today's session, are involved in FAMI as well. So finally, a quick plug on the behalf of FAMI. So FAMI is organizing a couple of further events this year in addition to this one. So we've been running a free online symposium for 2 years now. We'll do it again this year in December, sorry. And there will be also an in-person workshop in Marrakesh in Morocco, and that's on the 10th of October. So thank you all for listening, and I'd be happy to take any questions.
Thank you very much, Dr. King. We have learned a lot about fairness, and thank you for your time and for sharing with all the risers. So now we are opening for some questions. We saw you post some in the chat, but I don't know, should we read them or should we open the mic? Should I read it? Okay. Okay, I'm just going through the chat. Okay, so here I have one from Anis. He says, should we omit the use of certain variables like race when training fair models, or instead try to balance the data?
No, that's a very good question. So it comes back to the point I made earlier on, that if you tell a doctor to ignore somebody's race or to ignore somebody's sex when they're trying to diagnose a disease, they would think you were crazy. So I think personally that it's crazy to hide that information from AI models as well. I mean, it kind of depends on the application. I should qualify that slightly. But I think this is a key difference, I think, of AI in medicine and AI in computer vision. That I don't think we should be ignoring this information in medicine. I think it's useful information, but we do need to think about discriminatory behavior of the models. Balancing models is definitely a good thing. Certainly boosting underrepresentation of minority groups is a good thing. But there's lots of work actually that shows that even if you have 50-50 splits between races, you don't end up with a fair model. So even then the problem doesn't go away. It's much more complex than that. But it's definitely a good thing to get data from underrepresented groups.
Thank you. Now there is another from Joey. He says, before we enforce fairness in the task, either pre, in, post model, probably should we verify whether the chosen feature, like race, sex, etc., should be treated fairly? And then he asked, what if those features might be crucial factors for the task? Otherwise, there is a chance to be far away from the truth by applying fairness techniques.
Yeah, so I think that's kind of linked to the last question, really. That I think if you hide this information from doctors, they wouldn't be happy. So it often is useful information. You know, if you ask a doctor to diagnose skin cancer, you know, without knowing what somebody's race is, they would think you were crazy, because, you know, malignant skin cancers are much less common in darker skinned people. So that they know that, and they use that information when they're making diagnoses. Same like breast cancer is obviously much more common in women than in men. And so if you ask a doctor to diagnose breast cancer without knowing the gender of the subject, they would think you were crazy. So I think we'd be crazy to hide that information from AI as well.
Thank you. Then we have another from Afsana, is asking, is domain shift the same as concept drift in ML?
Oh, that's a good question. So there's an answer to that one there as well, I think. I think Islem has already answered that one. I don't think it is exactly the same, but I'm not completely familiar with concept drift. Islem, do you want to answer that one? You've answered it already.
Yeah, so I wasn't very sure because there are different. So I'm familiar with domain fracture and so is the question about the domain fracture, right? Domain drift, fracture, and shift. So in machine learning, when there is a shift in distribution between the training data and the testing data, so they have different distributions, we call that domain fracture, shift, and also the domain, yeah, so fracture or shift or drift also, yeah. So but it depends. So sometimes you can have also heterogeneous distributions in the training itself, so that's a different problem. So here I think it's commonly to use the word shift, domain shift, when you have a shift between the training data and the testing data, but it could be more complex. Yeah, thanks.
Thank you, Islem. Now we have another, again, from Joey. He's asking, do we focus mainly on demographic features in FAIR AI in medicine? And do we only focus on the protected features?
Yeah, that's a very good question as well. So we call them protected attributes because it's illegal to discriminate against these people by law in most countries. You know, then I don't know about other countries, but in the UK we have the Equality Act where it's illegal to discriminate against people by sex and race and disability and lots of other things. So that's why they're protected. But there are other attributes which are not protected by law, which we might also want to ensure fairness for. So I think that's something which has been mostly overlooked by the field at the moment. So I was saying earlier on, I think there's much more to do in this field. I think that's something that should be looked into more in the future. So for example, it's not illegal to discriminate against somebody by their BMI, for example. It's clearly not a good thing to do, but it's not illegal. There's nothing in UK law that says that you can't do that. So that's a non-protected attribute, but it's arguably an attribute that we should be trying to ensure fairness for. And there's other things as well, like pathologies. There's nothing in UK law to say that you can't discriminate against somebody by what disease they have. But we shouldn't do that, obviously. So yeah, I think I agree with Joey.
Now there's another from Ala Malik is asking, could you clarify why do we address and not mitigate, unlike computer vision? And also, what other ethical considerations are worth looking into besides demographics?
So mitigate, to me, mitigate means try and make it go away completely. The ideal case of bias mitigation is that the bias will disappear completely. But depending on what we mean by bias, I think some kinds of bias are not necessarily a bad thing. I don't know if that's a controversial thing to say. But so again, thinking about the skin cancer example, if we were to try and enforce the classifier to diagnose skin cancer with equal frequency in dark-skinned and light-skinned patients, I don't think that's good because skin cancer is much more common in light-skinned patients. And by trying to ensure fairness in that case, we would actually be making the classifier worse. So the bias that it had is actually clinically useful bias. It's clinically informed bias. So that's why I like to talk about addressing bias. Clearly, there's some types of bias are bad. Many types of bias are bad. But I think not all types of bias are bad. And so that's why I don't like to talk about removing it completely.
Thank you. Then that says, do you think the rise of large multimodal models trained on almost infinite data makes these fairness methods less relevant?
Well, so where is this infinite data in medical imaging? It's there in computer vision for sure. There's lots of these massive data sets. It's much more challenging to get these massive data sets in medical imaging. If we had them, then yeah, it's great to make use of them.
Then another from Indin Damola says, how do we identify research questions for FAIR AI in medical imaging?
Well, so I've mentioned a few in the talk, but I would say have a look at the literature. So if you look at the FAMI website, there's a section on the FAMI website called resources, where we've kind of picked out what we think are some of the key papers in the field. So you don't need to sort of trawl through the literature and find them all yourself. Just go through those. try and read them and try to understand them and see what are the key themes that are being addressed. And many of them will have weaknesses, and they will discuss weaknesses and future work at the end. So you can sort of take ideas from those kinds of areas and talk to people in the field. Come to events like this and talk to people in the field. I think in general, people that work in this field are there partly because it's an interesting subject, but also partly because we want to make the world a bit more fair. So we're not against other people working in this field. We don't see it as competition. Personally, I'm very happy for other people to come and work in this field as well. And I'd be happy to talk to people and share ideas.
Thank you. There's another from Umang. It's asking, synthetic data is suggested as a potential way to represent groups better. But if one uses the minority's same data to generate new data, are we not creating another kind of bias?
Yeah. So like I mentioned earlier on that you can use augmentation to sort of boost the representation of minority groups, and which is a nice idea, but actually it's arguable whether you're really introducing extra diversity, because it's all based upon the limited amount of data that you do have. I think so I agree with the comment. I think it's possible that with more sort of sophisticated generative AI techniques that we might be able to address that point a bit and actually get better at introducing true diversity using sort of these generative AI techniques. But it's a very good point that, if you've got a very small amount of data, then you clearly don't know much about the distribution of that data. You're very uncertain. And so trying to boost, to fill in the gaps, if you like, in that distribution is subject to uncertainty.
Then Abhishek is asking, how do we detect the existence of bias? Just by counting the class instances? Or what about more complex biases?
So in simple terms, you can compute things like demographic parity and equalized odds, these metrics that I talked about, and just compute them for different protected groups and compare them. That's the simple thing to do. One thing I haven't mentioned much is about intersectional analysis. So sometimes you might not see bias in protected groups, but then when you look at intersectional groups, like for example, so by intersectional groups, I mean more than one protected group. So it could be, for example, Black women or white men. So they're both intersectional groups. So sometimes you don't see bias in the original protected groups, in single protected group, but then you do see it in intersectional groups. So you just have to, it's kind of detective work, really. You have to sort of just look at many different groups and intersectional groups and many different metrics and just really understand what the performance of the model is and how it varies between different groups.
And Ulrich is asking, are there any examples of industries or applications where fair AI is being successfully implemented?
Yeah, I'd like to know the answer to that question as well. I hope so. I think with the forthcoming AI legislation, so it's coming into force. We have they have an AI Act in the EU coming into force over the next 3 years. I think the United States also has something. We might have something in the UK, you never know. But all of these acts, they're talking about bias and fairness as one of the things that need to be ensured. So for example, the AI Act in high risk, the EU AI Act, in high risk applications, of which healthcare is one, it will be illegal to have bias in your model in a few years' time. So I think companies are becoming more aware of that. They're not always open about what they're doing, what they're doing about it. But I think eventually, in a few years' time, they're going to have to show that their models are free of significant bias before they can deploy them. So if I was working in industry, then I would certainly be focusing on that. I don't know if anybody else on the call that works in industry wants to comment.
Yeah, I mean, I work in industry, and yes, it's something that we are actively looking, and yeah, it's still, as Annie mentioned, there's not clear guidelines, so this is one of the things that limit it, and it's like a bit of a gray area, but it's something that definitely many companies are looking at currently.
Thank you. And now this is the last question, and it is asking how to train a model to ignore certain features. Does using data augmentation help? Using even unrealistic data for those features?
To ignore certain features, you mean like race-specific features or protected group-specific features?
Anis, could you extend, please?
Yeah, so I mean, I think this happens. I think it's shortcut learning, basically. The reason why a lot of these biases occur is down to shortcut learning. So I don't know if you're all familiar with the term shortcut learning, but in shortcut learning, if you, for example, train a dog and cat classifier and all the dog pictures, they have the dog on the lead, then the AI model will not necessarily learn to spot the features of dogs. It will just learn to spot a lead, and it will say that anything with a lead on it is a dog. And then if you give it a picture of a dog without a lead, then it won't recognize it as a dog. So it's found a shortcut that gives it much better performance than actually the hard task. And I think a lot of these biases come from finding shortcuts, and they're protected group specific features that it's shortcutting on. So the more the diversity you can have in the data set, then the less likely these shortcuts are to occur, I think. So I think it's all about diversity and representation. I don't know if that answers the question.
So thank you very much. And thank you everybody for your questions. And again, thank you very much, Dr. King. We really thank you for your time. Yeah, oh, there isn't one last question, sorry. He says, Nikolai, is there any chance to learn something from the unfairness of a model? Is there maybe a medical reason for different behavior?
Yeah, absolutely. Yeah. So this is why I was talking about addressing bias. And so it is, you're right, it's a way to understand things as well. But still, it's useful to be able to measure the bias and really understand the performance of the model. So I don't think it's enough these days just to quote accuracy figures for classifiers. I think you need to dive into it in a lot more detail. And then you might find new insights, as Nikolai said.
Okay, so now we're gonna finish this first session. So before we go for a break, we would like to take a picture. So if you could please open your camera. This will be for our host and for our site. So, and then we can all see together. So that's always good. Okay, Islem, do you take the picture or should I?
We can all take pictures and then
Okay.
choose the best. Lots of screenshots. Let's wait
Okay.
for more people to kind of turn the cameras, and then yeah. Thank you guys.
Okay, so I guess now we're almost all.
I think we can wait a bit more, and it's like we have two screens actually, so
Yeah.
take two different screenshots. All right, awesome. You can do the counting, Andrea.
Okay. Okay. So we're gonna do the first one. So 1, 2, and 3. And now we're gonna take another one. So 1, 2, and 3. Okay. So thank you very much, everybody. And again, thank you, Dr. King. So now we're gonna take a 5-minute break before we start the second session, where we're gonna talk about the case study and start like doing some work. So yeah, so we will start again at what will be? So here is 9:45, but like in 5 minutes. Yeah, thank you. We start the recording. Okay, so for that, we're gonna create some breakout rooms. I'm gonna assign it soon, but first I'm going to introduce who's presenting this session. So she is Dr. Esther Puyol, and Dr. Puyol received her bachelor's and master's of science in biomedical signal processing from the Polytechnic University of Catalonia in Spain. And during her studies in Spain, she enrolled in a double degree program with Telecom Bretagne, where she obtained the French Masters of Engineering and a Research Master's in Medical Imaging in 2014. In 2018, she obtained her PhD degree in biomedical engineering from King's College London, and her research focused on developing a multimodal statistical atlas of heart function from cardiac MR and ultrasound imaging that could be applied using only low-cost ultrasound imaging. And currently, she is working as a research scientist at Heartflow, where she develops algorithms for cardiac segmentation. So please welcome Dr. Puyol.
Thank you very much, Andrea. So thank you, everyone. Hope you enjoyed the lecture given by Dr. Andrew King. I think he has given us a very nice overview of the area of fairness. But we also thought that in this summer school will be very important to have a hands-on session. So for that, what we are going to be doing now, we will be, as Andrea mentioned, breakout in different rooms. And in those rooms, you are going to have access to different case studies. So for that, what you can do, I'm going to share quickly the screen just to show you. But if you go to the GitHub repo, which was posted in the chat before, and you go to day 1, so Fair AI in medical imaging, you will see here all the different scenarios. So in each breakout room, you will be discussing 1 or 2, most likely. But if you want to download them beforehand, so you can start reading. And the idea will be that for a half an hour, more or less, you will be discussing one of them. So in this scenario, you're going to be presenting with a case. And then the ideas will be to discuss from your point of view what is important in terms of fairness and how it would be possible solutions to mitigate them. And then what we are going to do is we are all going to come back to the main room. And what I would like to have a representative per group, which is going to give a very brief summary of the case study and also propose or explain what has been the discussion that's been going on in this group. So yeah, I think without further ado, we can go into the breakout rooms, and then yeah, you can start all these discussions.
So
So
now
do we have
they're
the
open.
breakout rooms
Oh.
or?
Yeah, I just
Okay.
read. Yeah, and I assigned them, so please just join your breakout
We
room,
have
please.
only 2, right?
No, we have 9.
9. Oh, okay. I see them now. Okay, thank you. Sorry.
Yeah, no worries.
Okay, I'll join also 1.